Hello and welcome to this video example. So for this lecture or example, we will be discussing second order. Let's put a 4 in there if you don't mind. So example for second order homogeneous LTI ODEs. So for this particular example, let's say that we're asked, as we generally are, to find the system response, and we're given the following differential equation. D squared x dt squared plus 2 dx dt plus 2x is equal to 0, and we're going to have some initial conditions. So we will have that the value of x at t equals 0 is equal to 7, and the initial value of the derivative dx dt is equal to 4. So when we're looking at this particular differential equation, we can just, understanding that it's an LTI ODE, we can just go ahead and write down the characteristic equation. Let me give myself an arrow there. So we understand that when we take the second derivative, we're going to end up with an s squared. When we take the first derivative, we're going to end up with an s. And so we can see that the powers of s, based on the assumed solution that we discussed in the lecture, the power of s maps to the order of the derivative. And we didn't take any derivatives for the first term, and so then we just get a 2. And of course, we've already seen where the characteristic equation will be equal to 0, clearly for these homogeneous cases. So let's go ahead and look at the roots associated with this characteristic equation. So we get s1 comma 2, and that's equal to square root got a little big there, my apologies. Square root of, hey, and I don't need the square root first. Boy, I'm really messing up. I really want to take the square root of something. So we have -2 coming from -a plus minus square root. Now I can finally write it up there. Minus a squared, which is 4, minus 4 times b, not squared, which is 2. And all that divided by 2. And so we can see pretty quickly that we end up with a -1 plus minus 1/2 times, so we get a 4 minus an 8, well, that's a -4. So we get -4, root -4. But of course, we can factor out the negative sign and get a j, and then the square root of 4 is just 2. 2 divided by 2 is just 1. And so we get -1 plus minus j1. Now, some people will just write J. That's perfectly fine as well. But nonetheless, I generally like to write the magnitude associated with the complex component explicitly. And again, I'll just remind you that J is equal to square root of 1. So as you can see, it's pretty easy to develop the characteristic equation for this kind of differential equation, and you'll soon come to appreciate that this kind of differential equation is really one of the nicest ones for you to work with because they are so easy to solve. The solution framework that we developed is just really amazing. Because now that I have my real component and my imaginary component, I can simply write down my solution. So substituting in for sigma and for omega, we get that x is equal to e to the sigma t, in our case, sigma is -1 times t, times c1 times cosine of omega. Well, in our case, omega is just 1 times t, because remember, this is omega right here. This is, of course, the magnitude of sigma, plus then c2 sine 1 times t. And there we go. We have our solution. Now, of course, we can write it in a simpler fashion. That's exactly what I'll do. E to the -t times c1 cosine t plus c2 sine t. So that's our solution to that differential equation. Makes perfect sense. I substitute that into this solution into that differential equation, and I will get 0 equals 0, provided I do all my math properly. And of course, we'll see that here in a moment. So the one thing that we have left to do, though, is we have to find our initial conditions. So let's go ahead and do exactly that. Actually, let me show, before I do that, I kind of, since I've said it, I kind of want to show you that this is a solution. So let's do a little aside here before I move on to the initial conditions. So I said that this is a solution to this particular differential equation, again, regardless of the initial conditions. So let's go ahead. We have our x here, so let's go ahead and find dx dt. So dx dt is equal to, using the product rule, taking the derivative of the exponential function. We get a negative e to the -t. That's a little hard to say. And then we, of course, don't change anything in the parentheses. Cosine t plus c2 times sine t. And then now we have to take the derivative of what's in the parentheses, so plus e to the -t, all that times now negative c1 times sine t plus c2 times cosine t. So that's our first derivative. Now we also need to take our second derivative, and of course this is where things get a little painful, but yeah, that's okay. And so we again take the derivative of the exponential function first, and we get a -1 times a -1 gives me a +1. And then we don't do anything initially with this stuff in the parentheses. So let's go ahead and just rewrite that. And then we have to take the derivative of what we have in the parentheses. And of course, that's just going to be exactly the same as what we have in these parentheses, except it's still going to be multiplied by a negative e to the -t. So we have a negative e to the -t now times our negative c1 sine t plus c2 times cosine t. Now we have to do the same thing, but for this term. So we get now starting with this exponential function, a negative e to the negative t, all of that times, and here we haven't changed anything in the parentheses, so we get a negative c1 cosine. Oh, sorry, I got off by one line. Times sine, there we go, of t plus c2 times cosine of t. And then taking the derivative of what's in the parentheses here, we get, so we keep the exponential function the same since we're not taking the derivative of that, and then we get a negative c1 cosine of t minus a c2 times now sine of t. Now, of course, and if you'll let me do some kind of electronic math here, we can go ahead and factor out this negative sign. And when we do, we end up with a negative out in front here. Guess I didn't have to erase the negative sign. And the reason I want to do that is because what can you see? You can see that these two terms are identical, except one is positive and one is negative. And so, of course, this will cancel with this. These two are the same, so we can just combine those and we get that dx squared, or d squared x dt squared, is simply equal to negative 2e to the negative t times negative c1 sine t plus c2 times cosine t. So now let's go ahead and substitute into the differential equation. So substituting into the differential equation, we get negative 2e to the negative t times negative c1 sine t plus c2 times cosine t. Then we have 2 times the first derivative. So that gives us a negative 2. I'm just going to distribute the negative 2 on out. So a negative 2 e to the negative t times c1 cosine t plus c2 times sine t. I think I'll be able to squeeze that in there. There we go. Perfect. And then we have a plus 2 times e to the negative t times a negative c1 sine t plus c2 times cosine t. And then last but not least, we have 2 times x. So plus 2 times x is e to the negative 2, oh sorry, e to the negative t times c1 cosine t plus c2 times sine t. And so we can clearly see that this term is identical to this term, with the exception magnitude-wise. The exception is, of course, that they are of opposite signs, so this will cancel with that. And we can see the same thing. This term, I shouldn't say magnitude, maybe magnitude's fine, but this term is, of course, exactly the same as this term with the exception of the sign. And so, of course, this term will cancel with this term. And, of course, that means that this whole thing is equal to 0, just as it had to be. Okay, so now I've shown you that this relationship for x is a solution for the differential equation, regardless of what C1 and C2 are. Doesn't matter. But we also have to find what C1 and C2 are. So let's go ahead and find the initial conditions, or find the values of C1 and C2 that properly capture our initial conditions. So we have x at t equals 0. So here I'll just kind of bring that down. X at t equals 0. Well, plugging in t equals 0 to this, plugging in t equals 0 into this expression, clearly the exponential function just becomes 1. It's raised to 0. E is raised to 0, so it just becomes 1. Then we get a C1, and then we get a cosine of t equals 0. Cosine of 0 is just 1, so we get a 1. And then we have a C2 times sine, but now this is sine at time equals 0. Sine of 0 is 0. And so we can see that we get C1 here, and we can also see that based on the problem statement way up here that x naught is equal to 7. So we can see immediately that C1 is equal to 7. Now additionally, we have the expression for the derivative, and we need to evaluate that expression for the derivative at t equals 0. Well, here's the expression for the derivative right here. So again, we plug in t equals 0, and what do we get? We get, for this first exponential function, we get e raised to the 0 is 1, but it's negative e raised to the 0, so it's negative 1 times c1 times cosine at t equals 0. Well, cosine 0 is still just 1, plus then c2 times sine at time equals 0. Sine of 0, that's still just 0, plus then, so close the parentheses, plus then, so now going to the second part of this expression, again, we have e raised to the 0 is just going to give me a 1. Now times a negative 1 times sine t equals 0 is just going to be sine of 0 is 0, plus c2 times cosine t equals 0 is just cosine of 0, and that's just 1, and close parentheses. And so we can see pretty quickly that we're going to end up with a negative C1 plus C2. And that is equal to the initial value of the derivative. So going back up, the initial value of the derivative was 4. So going ahead and setting that equal to 4, we quickly see that C2 is equal to 4 plus C1, and that is equal to 4 plus 7, since we already found C1, and that's 11. So plugging those values for C2 and C1 again into this expression for x, we see that x is equal to e to the negative t times 7 times cosine of t plus 11 times sine of t. And that is our solution that solves the differential equation, does two things: solves the differential equation and properly captures the initial conditions. So with that, hopefully this has given you a better understanding of how to use this solution framework in order to solve a differential equation, specifically a differential equation that has initial conditions or boundary conditions associated with it. The steps for this kind of homogeneous, let's be specific, the steps for this kind of homogeneous differential equation is really quite simple. You find the characteristic equation, you then find the roots of the characteristic equation. Based on those roots and based on the expressions that we've already developed for the 3 different cases, you just go ahead and substitute the values from the root or the roots into those expressions, and you build the proper solution for that differential equation. Then you just come back in and you plug in the right value or the values associated with the initial condition, value of time associated with the initial condition, and the values of the quantities also associated with those initial conditions. And you go ahead and solve for those constants. And that's really all there is to it for these particular types of problems for this particular class of differential equations. So with that, we'll call this video example a wrap.